Hello Pythonista. Now we are ready for our next session, getting to 3 million lines of type-annotated Python. And the presenter for the session is Michael Sullivan. Michael is, as he says, a recovering academia. Please welcome Michael.
Hey everybody, I'm Michael Sullivan. I'm going to be talking, like she said, about getting to 3 million lines of type-annotated Python. I'm here from Dropbox, where we're a very big user of both Python and type annotations. So sort of the way this is going to look is I'm going to just give a lightning-fast overview of Python typing and how MyPI fits into that. Then I'm going to talk about how Dropbox got much of our code base annotated. And then I'm going to talk about what we did to keep up with our success and make sure that performance stayed acceptable, to make sure that the performance is also lightning fast. So okay, that overview of MyPI. So what MyPI is it's an optional static type checker for Python that allows you to write type annotations in your Python code and have a tool before you run it, check it to make sure that those types make sense, which helps you prevent a lot of bugs and in a lot of cases makes it easier to reason about your code. So here's sort of the basic example of typing in Python straight from the MyPI website, which defines a function that computes the first n Fibonacci numbers. And so it takes in an integer for how many to compute, and then returns an iterator of ints back. It yields all the numbers and gives integers. The sort of style of typing that Python uses was defined in a Python PEP called 484. So if you hear that mentioned, that's sort of the definition of Python typing. Now, this example here is using sort of syntactic type annotations, which were added in Python 3. But like a lot of people, Dropbox hasn't gotten rid of all of our Python 2 yet, or honestly even gotten that close. So MyPI needs to be able to support Python 2 as well. And it does that through this workable but not beautiful technique of type comments, where you write sort of a comment at the top of your function saying what the type of the function is, and the type checker will be able to figure it out from that. It's not beautiful, but it works. So that's what we do. So what's an example of things that the type checker can do for you? Here's a pretty simple one. We define some function called foo and say that it takes a parameter that's a string. Then we try to call a method on it called eggs, but strings obviously don't have an eggs method, so the type checker will complain at us. It'll say, stir does not have attribute eggs. Or let's say we try calling that function with none. We will then say, OK, but this function wants a stir, and we're passing it none. That doesn't work. This is nice because it gives sort of a level of checking that a lot of sort of more traditional statically typed languages don't have. For example, in Java, basically any object you could pass a null in instead, and something breaks at runtime. But the sort of Python equivalent of that, none, will catch. Importantly, all of this is done statically beforehand without ever running the code. MyPI does all these analyses. Importantly, for the sort of MyPI type checking process, you don't need to type everything all at once. It's very important that you be able to mix typed and untyped code, which allows you to gradually add type annotations to your code base. If you had to do it all at once, that would be deeply intractable because we have 5 million lines of Python or something. We can't add types to it all at once. That would be sort of, one, impossible to do, and two, sort of too big of a change to land all at once, even if you sort of could do it. So here we've got functions foo and bar, and foo has a type and bar doesn't, and they work together just fine. So that's sort of the basics of type annotation. Now I'm going to talk about what we did at Dropbox to sort of advance this, to get it into our code base. And so the first question about how to annotate legacy code bases is, why even bother? That sounds like a lot of work, and it's work that we're doing maybe instead of writing new code. Why not just annotate new code and leave the old code that works unannotated? And the main reason for that is that interactions with untyped code can't be type checked. If you're working with code that doesn't have type annotations, MyPI just has to assume that it can be anything. You sort of can't make any assumptions about it because you don't know what it is or what it does. which means that any new code you write, if it's interacting with old code that doesn't have type annotations, you lose a lot of the benefits of typing. The more of a code base has type annotations, the more benefit that typing gives. It's sort of a nonlinear payoff. Like once you get a ton of your code base typed, then it's really good. Whereas like if you only have some of it typed, it's, just kind of good. In MyPI itself, which is written all in Python and type-annotated Python, we have basically 100% type coverage. Every function in MyPI has a type annotation. And this allows us to rely on type checking to support a lot of aggressive operations in the code base. We can do major refactors, renaming things, changing the types of things, like large changes. And when we do it, we expect that the type checker will tell us most of the places you need to change. If you add an argument to a function, before we even run tests, the type checker can say, like, OK, here are all the call sites you need to update. So then what do we do to get this done? How do we get old code annotated? And to quote Mike Sullivan, a senior principal engineer at Dropbox, when we asked him for some advice, he said, show value, reduce friction, encourage the general virtuous cycle, and when all else fails, move the mountain yourself. Well, OK. So what are some of the ways we did that? One of the first things, and one of the core things we've done a lot of is trying to talk to our users to make sure what they want out of MyPI typing and what's causing them trouble. So we do about twice a year a regular MyPI survey where we ask a lot of questions of our users about, how much do you like MyPI? Would you recommend MyPI to a friend? What are your biggest complaints about MyPI? And sort of gratifyingly, the biggest complaint that we get these days is that not enough code is type annotated. People want more MyPI, which is great. We'd love to give them that. And then something we got a lot last year but stopped getting this year is performance. We'd like MyPI to be faster so we can use it more and have it be less invasive in our workflows. So as part of trying to get more typing, we've had a lot of meetings with teams where we sort of try to figure out what's keeping them from typing their code and push them to get things working. So one common thing we've heard with teams is like, oh, well, we'd love to use MyPI types, but we don't understand how. We've got some complicated library that has some sort of typing behavior that we don't know how to express with MyPI. There's just not a good way. And well, MyPI has a plugin API. We can help people build plugins to make their stuff work. We've built a plugin for SQL Alchemy and adders and data classes that are all public, and then a couple for internal Dropbox libraries too. Even old code can sort of be worked into the model with our plugin system, even code that doesn't sort of naturally fit a type system. Another thing we get told a lot is we're asking teams like, hey, maybe you should annotate your code. And they tell us, well, we'd like to annotate our code. We like types. But the thing is, we have our quarterly goals, our OKRs or whatever, and typing code isn't on them. And it's not clear that we can get more of our code annotated because none of the teams using our libraries have been asking us for it. Well, we know that a lot of teams want this, so we can sort of make sure that their users know who to bother about it. Like if web platform doesn't have type annotations, we can make sure that all of their consumers know, hey, look, ask them for them. They might be able to do it. As part of figuring out what's worth annotating, one of the big things we've sort of needed to figure out how to tackle is that not all annotations are equal. Not everything has the sort of same value to annotate. If something is called 1,000 times, it's more important to annotate than something that's only used in one or two places. Because if it's only used in one or two places, the sort of impact of not having type information is very small, because there just isn't that much downstream of it. But if something is used 1,000 times, then every single place that calls it, even if all of those have type annotations, they aren't getting any information. They don't know what it is. Whenever they operate on it, we can't find any mistakes there. So a missing annotation reduces how useful type checking is in all the code that uses it. And so anything with lots of uses is a big, valuable target for getting annotated. But there's sort of a dark corollary to that, which is that the most important functions to get type checked are often the hardest to type check. Not because there's sort of anything fundamentally hard about giving them a type, but because if they have lots of uses, then it's much more likely that lots of those uses will have errors. If something only has one or two places that call it, and one of and like 20% of the call sites are wrong, that's, like 0.2 call sites on average you need to fix. That's not bad. But if it's got 1,000, and now you've got to fix 200 bugs, it's sort of, you'll very quickly decide like, oh, maybe it's not worth fixing this because it's going to be super tedious, even though it would help a lot. And so that's something we actually still struggle to find a good trade-off for, because it's hard, but something worth tackling. As part of the sort of getting teams to do the work for us and to sort of encourage the cycle of type checking, we send out weekly email reports to about 50 teams at Dropbox, sort of giving them information about the state of type annotations in their code bases based on sort of our notion of ownership. So teams get emailed saying, hey, like 40% of your code is typed. Maybe you should try to type more of it. Here's, like what you've gotten typed recently. Here are the good things. Here are the bad things. And here are some functions that we think are very important for you to type. The ones that have lots of use sites that are typed, like we were talking about before. Now, unfortunately, it's sort of hard for us to tell like how much these emails help. Because it's hard to track sort of a direct correlation between any changes and, the emails we're sending out. So it's hard to get an exact metric on that, but as a bit of signal, shortly after we started sending out these emails, we got contacted by a bunch of teams who were like, hey, these emails are great, and we'd really like to use this reporting information to sort of directly decide how to change our code. And so could you give us sort of a self-serve way to do it? And so we built that, and it's become, I think, popular, at least in a few teams. We also had sort of a very gratifying bug discovered in this reporting, where the first team at Dropbox to reach 100% coverage on their code sent us a sort of very satisfying email saying like, hey, we found a bug in your report generator where it gives nonsense information if you have 100% code coverage. We're like, huh, yeah, we didn't think anyone was going to get there for a while. We never tested that. And the sort of I've been talking a lot about sort of the social pressures we do to try to get annotation done. Now I want to talk about some more of the technical measures we do. And this is here sort of at the intersection of technical measures that we're doing to sort of apply the social pressure to get things working. So one thing we have is we have a linter that complains whenever you add a function that doesn't have an annotation. And we recently sort of turned up how annoying that linter is. At Dropbox, we have different linter complaining levels, and previously it was a notice, and we've now moved it up to a warning. And whenever a linter gives a warning, in our system, you have to type in an excuse for why you're ignoring it. And so it's not hard to ignore, but it takes just like an extra 5 seconds and one more step in the process. And so you do it, and you're like, oh, okay, maybe I'll just fix it. Like, it'll take a little longer than like writing out a good excuse, but not that much longer, maybe. And as part of that we're trying to gradually ratchet up the default level of enforcement. By when we want to introduce some new check we'll make it the default and then sort of automatically opt out code that doesn't check. So pretty soon we're going to be making you must annotate your code be the default, and anything that doesn't, we'll be able to opt out, but setting the right defaults is a big part of this. Now, sort of moving into more explicitly technical measures, things that are just a technical device for getting code typed. Sort of one kind of clear observation is, these types should match Python runtime types. Like if something's an int, that's a Python thing at runtime, it's an int. And Python has pretty deep introspection facilities, so you can at runtime check what types things are. So you can imagine, and we did, building a library that sort of dynamically at runtime records the types of all the inputs and returns from a function, and sort of outputs that to a tool that can add those annotations to the code. So we built a tool called PyAnnotate to do this. But honestly, it didn't help us that very much. Like we have not had a ton of luck with it. This is one of our losses, maybe. And a couple of the problems we had is the loads in test cases are pretty unrepresentative of real types. Like instead of some real object being passed in, like probably it's mock. And so you sort of don't get the data you need. And so really you need to sort of run these on like real loads, like maybe live site loads. But like some, like 1 out of every 100,000 requests or something. and sort of gather the data from that. But unfortunately, our team itself sort of lacked the expertise or the confidence to go insert sort of this invasive monitoring stuff into like live Dropbox site loads. And we had some troubles getting buy-in from the parties that did have that expertise, partially because we didn't want to push that hard. But there was some nervousness about it, so it sort of never got off the ground. And so because we sort of never had those bulk data collections, it couldn't really be done in batch. It produced output that usually required tweaking, and we had troubles getting engineers to do much uptake for it. That said, other people have had success with this. I know that there are it's an open source project, and we have open source community users. And Instagram has reported success with a different tool that they built called MonkeyType to dynamically monitor Python types and generate type annotations from them. And my understanding is that they did set up the sort of live site type recording that we never got around to. So if dynamic inference of type annotations doesn't work, maybe the other thing, right? We've got a type checker, so we might just be able to look at the code and sort of via program analysis figure out what can happen. And so that actually works okay. So as a really simple example, here we've got a function called foo that just adds 1 to its argument, and some other module b that calls it. And so we can look at the program and say, like, okay, every place that calls foo is calling it with an integer. So I guess that probably means that the input to foo is an int. And then once you've assumed the input to foo is an int, you say, like, okay, x is an int and 1 is an int. And if you add them together, that's also an int. So the return type must be int. And once you've computed that, you can sort of check to make sure it works and that it doesn't produce errors, and then say, like, okay, I guess that's the type of the function. We can write that in there. And sometimes it's trickier because there might be different functions getting called, and there are like different options for how you can combine them. So we'll make up a couple different possible function types, see which works, pick the best. But this is a reasonably productive approach. And so we have just, in the last couple weeks, started automatically adding statically inferred type annotations to our code base. It's still a process that requires somebody to sort of shepherd it through to generate a diff and put it up and get approvals. When I first tried this, I generated a diff that was way too big, that added like 3,000 annotations all over the code base, and I put it up without thinking as hard about it as I should have, and then I go look, and it's emailed half the engineers at Dropbox asking for code reviews. I was like, okay, well, this was a mistake. Sorry about that. One of the next steps, because we don't just want this to be a tool for me to add type annotations, we'd like other people to be able to leverage this too, is to build a user tool that fits into this, maybe with some IDE integrations that'll say, like, hey, here are like the best guesses we have for this function. We haven't found anything that's perfect, but like here's what works well, and maybe here's what you have to tweak. So I've talked a bunch about what we've done to get our code base annotated. And so there's the question, like, how's this working? Are we getting it done? And the answer is, yeah, it's going great. Here's a graph over time of how many lines we have annotated in our server code base. And it's this nice up and to the right graph, right? We started off with nothing back in 2016, and now we've got 2.5 million lines in just that repo. There's a catch to this, though, which is that here's our performance graph. Here's how long we take to do a total type check of the repository. And it is also this very clear up and to the right kind of graph. So now I'm going to talk a bit about what we did to keep up with our success. Just going back to that graph, because I just love this graph. I mean, I don't love it. But I love just how nicely clear of a linear relationship it is, right? It's like, this is how much code we're checking, and this is how long it takes to check. And every so often you can see oh yeah, we messed up and it started getting nonlinear, and then we fixed it, but it's still going up. And so, I mean, this is obviously a problem. And it's been a problem for this whole time, and we've been doing things to mitigate it that aren't reflected in this graph that I'm going to talk about a bunch. So at its worst, MyPI was the long pole sometimes, about 20% of the time, in our continuous integration system. The long pole being the slowest part, the part that, when you've parallelized things, you can do a bunch of things at once, but there's still no way to be faster than the slowest thing. So if MyPI takes 25 minutes to run, in order for something to get landed into our repo, then nothing can land faster than 25 minutes, which is real bad. On top of that, this is obviously really painful to use as part of interactive development. Not only can you not reasonably use something interactively if it takes 15 minutes, honestly, if it's at 2 minutes, that's way too bad. So, and on top of that, fear of making this problem worse sort of limited how hard we could push on growth. It was always sort of this trade-off, like, okay, we could go sort of do a bunch of stuff to automatically add annotations, but if that makes MyPI take twice as slow, maybe we need to focus on performance first, which happened a bunch. So I'm going to talk some about the strategies we've done to approach this. And two of them are pretty straightforward, doing incremental type checking and using caching. And then one that's maybe a bit more off the wall, which is we built a new compiler for Python and for type-annotated Python in particular. So, OK, first, the incremental type checking. There's sort of a trivial idea that the easiest way to compute faster is to compute less. If you have less computation to do, it obviously will go faster. So the idea is, instead of checking the whole code base whenever we run, we should only check what we have to. So the idea then is we store type information to disk when we run. We store sort of a cache of what all the different types we've seen and what modules have what functions and all of that. And when we run, we check just the files that have changed. And then once we've checked the files that have changed, we check any modules that depend on modules that have had interface changes. Here, when I say interface changes, our idea of interface for this is actually kind of cute hack, which is we generate these cache files saying, like, OK, here is all the relevant things about a module, all the functions in it, all the types of those. And so the interface we check is actually just a hash of the cache file. If the cache file we generate changes, then we know the module's changed in an important way, and we need to recheck anything that depends on it. So this works pretty well. There's an unfortunate snag, which is that for annoying technical reasons, if you have an import cycle, like modules importing each other in a circle, those need to be checked all together. So if one module in an import cycle has a dependency change, you have to check all of those. And if you have like a nice, elegant, beautiful, well-factored code base, this isn't a problem at all, because you shouldn't have big import cycles, because that's a pretty major code smell. We have some pretty big import cycles, like high hundreds of modules. And so whenever you had to hit anything that needed to check that, it got bad. OK, so here was supposed to be a graph of how incremental mode improved the typing, but instead this slide is intentionally left blank because I was having troubles finding our historical data for it. But this helped a lot. It ends up being a pretty substantial speed up, if thing like 4 or 5x for the typical case. And when we were doing this incremental mode, it got the sort of, at the time, MyPI took about 8-9 minutes to check the whole repository, and with this incremental mode, it would get down to 1 or 2, which was solidly usable in most interactive cases, just not good, but it was not impossible. But there are still some bad things. So the thing about like doing stuff incrementally is you still need a starting point, something to increment. So you need to, at some point, generate that initial type information, that first cache, which requires doing this full check that takes maybe 10, 20 minutes. And you could say, like, OK, that's fine. Every developer runs that once when they start at the company, and then they've got some place to start from. But that's bad, too, because the changes when you switch between branches or when you pull all of the changes that other people have made can be pretty big. And you don't want people to have to type check, like, everybody else at the company's changes. You really want them to only have to waste time sort of checking their own code. So there's sort of a joke that like the only two systems-y ways to solve problems is to either add a level of indirection or to add a cache. And here, the trick is to add a cache. So we have our continuous integration systems. Every time a commit lands in master, it runs MyPI on it and generates sort of this cache of all of the type information in the code base. Then when users run MyPI, it will download this cache information sort of whenever they've done anything that we think might be a big change, like a branch switch or a rebase. So this gives us a cache that's sort of shared between all developers at Dropbox that's generated with a short 10, 15-minute delay. And this ends up being huge because it means that nobody ever needs to run these like full type checks. So this is great. Unfortunately, it isn't sort of released. Like the infrastructure to do this isn't released because it's much too dependent on the minutia of the continuous integration system and the build system and source control. Like we have a homegrown continuous integration system, and then we have sort of homegrown scripts for running MyPI and Git. And if you have any sort of different combination of those, the way you'd set this up is different. That said, it shouldn't be too hard. And our documentation does have pretty good instructions for how you might want to set this up. And if anyone's done that, I'd actually be really interested to chat with you to see how it's worked for you. Now, this whole cache warming also, there's a lot of sort of fun, very fiddly performance engineering we had to do, and what we were able to do to sort of improve it. One of the things that was sort of an easy win at one point where we were getting stressed out at like, oh man, it's taking like 6 seconds to download the cache information. Or like if you're in the Tel Aviv office, it's taking like 25 seconds just to download the cache. We were able to just switch the compression algorithm and get a good speed up. Another sort of dumb one was originally the cache was just a tarball of little JSON files. But the macOS file system is very slow at creating lots of little files. So if you switch to it just being one file, then it gets a whole lot faster again. We've done a lot of investigation on that sort of thing, like how to optimize all the details of this. Now, there are still some downsides to this incremental type checking stuff I've talked about. There's lots of data to load from the disk every time you run, because all the stuff is stored on disk in these caches. And the module is sort of a pretty big unit of rechecking because modules can be big and there's sort of a lot of work to do with them. You have to parse it, you have to reanalyze it, you have to do all this type checking. And so whenever something's dependency change, you need to do this full module reprocess. And actually worse than that, this full module reprocess of this entire cycle of modules, which at its worst would be like 500 modules at Dropbox, which is real bad. Like you'd hit that and it suddenly just gets very slow. So our solution to all of this is what we call the MyPI daemon, which is an incremental type checking daemon, which is to say like a background process. It runs in the background and does type checking for you. So instead of needing to load all the stuff from disk every time it runs, it tries to keep a lot of this information in memory. It stores syntax trees and the types of everything it's encountered sort of in memory where you can access them quickly instead of having to wait to load them. And then the way it works is, as we check the code, we compute what the dependencies are of every function and class that we encounter. So here in this example, we've got a function eggs in module B that's calling into a function foo in module A. So we track that b.eggs depends on a.foo. Then, if foo changes, so here the type's changed from returning an int to returning a str, we know that we need to recheck b.eggs. So we'll go recheck eggs, and we'll see that, oh, there's an error. We're trying to add a string and an integer. And we can do that without needing to sort of reload the rest of b.py. We don't need to parse it. We don't need to check spam. We can sort of just, because we already have it in memory, check eggs. So sort of the full story here is we compute the dependencies of every function and class. Then when run, we figure out just which files have changed. We recheck those files, and we figure out what functions and classes and type definitions have had an important change. And important basically means that the type has changed. If you change something about the implementation of a method, callers don't care, but if you change what types it returns, it's important. So from that, you then go and recheck everything that sort of depends on it. So anything that's changed, you recheck anything that depends on that, and then sort of push that outward. Like anything that those changed, you go recheck, and you repeat until you hit a fixed point. This involved some pretty exciting engineering because MyPI was really deeply not designed in the first place to allow this sort of rechecking and reprocessing. So there's some very fun, subtle code there, where fun is maybe a euphemism. But it works very well. So, and it was a pretty cool engineering achievement to get it to work. And then, like with the coarse-grained checking, we also use a remote cache so that you don't need to ever do a full check of the code base. Now, how well has this worked? When combined with what I'm going to talk about next, we get, on average, 75% of the time when our users run it, it takes less than 700 milliseconds. This is for like a 3 million line code base. When you need to start the daemon from the first time, it usually takes 75% of the time 50 seconds. And really gratifyingly to us, when we started rolling this out, and in the first place, it wasn't this fast. It was maybe 5 seconds, 6 seconds, down from a minute and a half. Users started using MyPI a lot more. Like as soon as we had this 5-second type checking, the amount of times people ran MyPI, according to our telemetry, went up by like a factor of 3. So as soon as we made it cheap, people started buying a lot more of it. It was great to see. There's a downside here, though, which is that it's still kind of slow for non-interactive workloads. It's still like full runs, which we had to do to generate those caches, would still take 15 plus minutes. And so it only checks about 2,000 or 3,000 lines of code a second, which when you're not managing to do this incremental stuff, isn't great. And so every so often, like, we'd have to disable incremental mode because there'd be some sort of bug. Like, we'd have generated a broken cache and needed to fix that. So we'd need to temporarily turn off incremental mode. And sort of our SLA ended up being for that, like, okay, whenever we need to turn off this incremental mode, it would usually take about 1.5 to 2 hours before the head of the developer effectiveness team would come over to my desk and be like, hey, Sully, when is MyPI going to stop being slow? And I was like, okay. That was rough. We wanted to avoid that sort of thing. So then the question is like, okay, well, why was MyPI so slow? Why would it take 20 minutes? And there are a lot of answers to this. I mean, one is just it had a lot of work to do. But the biggest answer is because it was written in Python. And obviously, everyone here, we all love Python. But Python does not have a reputation as being a speed demon. And that's for a bunch of different reasons. One of them, though less of a big deal than you might think, is just the interpreter overhead, the cost of having to look up sort of what the next bytecode to run is and dispatch it and sort of go through this interpreter loop. But that's definitely part of it. One of the biggest things is that attribute and method access is multiple hash table lookups, at least 2, sometimes more, like lookups in a hash table, just to access an attribute on an object. And that's rough because accessing attributes on objects is very common. And Python has like a very well implemented hash table, but it's still not super fast. So why is this? And like, why do we need to do all these hash table lookups and indirections to do everything? And the answer to that is sort of because Python doesn't have types. And so as maybe a history lesson of sorts, in sort of back in the 70s or 80s, when languages like C were built, they're statically typed, but the static types in C were basically all about helping the compiler. They weren't really there to catch bugs or provide safety. They were just there to tell the compiler how to lay out data in memory and what operations to generate. It was really about helping the compiler and not about the programmer. So as an example of that, if you have some C structure with a tag and a data field, the C compiler just turns that into a structure in memory that has a tag, and then 8 bytes later it has a pointer. And then on an Intel processor, at least, if you write p arrow data and try to access that field, that compiles into one instruction, just one MOV instruction. And now, instruction count isn't a direct proxy for performance, because modern performance is very complicated. But an attribute access in Python takes over 200 instructions on my laptop. And so, again, that's not a direct proxy for performance, but it's still quite a lot slower. And so there are lots of things that are sort of conspiring to make it slower, but this is really one of the big ones. So C types were designed just to help the compiler, and the types in Python, as envisioned by PEP44, were mostly not about helping the compiler. They're basically just designed to help safety checking. But that doesn't really need to be true. There's nothing fundamental about that. And in fact, PEP44 actually specifically says, using type hints for performance optimizations is left as an exercise to the reader. I was like, okay, well, I'm a reader. We can try this. So MyPI itself is, like I said earlier, basically 100% typed, which means we have all this type information that we could use to try to do this. And so the idea then is maybe we could write a new compiler for Python that takes advantage of all this type information. And now there's sort of this question of like, okay, wait, you're like a bunch of language and compilers people, and you think that the only way to solve a problem is by writing a new compiler. Like, should we trust you? And well, I mean, yeah, yes, I think so. Because just because all you have is a hammer doesn't mean that the problem isn't a nail. And it turns out this one was. So this was started by Yuka, the tech lead of MyPI, sort of as a side project, as a Hack Week project. That was essentially unfinished business from his PhD thesis, which was designing a Python-like language that was going to sort of compile to native code, but eventually Guido convinced him to turn it into a type checker for Python. But so the solution here then is we've built a compiler called mypyc. It compiles a subset of Python with what we call strict semantics, which means that the type annotations need to be accurate, and we can report runtime errors when they're not. So this ends up being basically a Python language variant because it doesn't run exactly the same, but it's very similar. And it uses MyPI itself sort of as a front end to do type inference and to generate the sort of input to the compiler. We then compile specifically to CPython extension modules, which are C programs or C libraries that get dynamically loaded by CPython to provide code that interoperates with Python but is written in C. And this is sort of the standard way to write Python libraries in C for either performance or to talk to system libraries. And one of the things is this sort of interoperates very cleanly with regular Python code. And so some people might notice, like, hey, this isn't the first time I've heard about this sort of thing. So what makes this different? Or to put it more colorfully, what about all the bodies of all the projects that have tried to do this and either failed or maybe not had as much of an impact as you might hope? And so Python works pretty well, but to get really good speedups, you sort of need to translate into their dialect and type system, which sort of thinks more about C types than it does about Python types. And we wanted to think in terms of Python types. PyPI is a tracing JIT that works very well for some programs, but the sort of program that MyPI is, it didn't fit very well. It doesn't have any sort of tight loops. It's sort of big, branching, very large, and we never had that much luck with it. Sort of more traditional JITs like Piston and Unladen Swallow sort of chose the full language support hill to die on, which is they wanted to be basically fully compatible with Python. And so then you spend all of your time trying to be fully compatible with Python and not enough of your time making it fast, and then your employers stop paying you to work on it. So we're not aiming for exact compatibility, though some of our gaps right now are kind of embarrassing, and we're working on fixing them. But so sort of as an example of what kind of code we generate, the big thing we do is try to provide good data representations. So if we have this class foo that, like our C example earlier, had a tag that's an integer and a data that's a string, we'll turn that right into sort of a C object that's a Python object and has sort of just laid out in the structure as C attributes a tag and data field. And then sort of as a, in the traditional compiler technique for doing method calls, we sort of also include a virtual table of function pointers that includes all the methods on the function. So you can call those without doing dictionary lookups, just by indexing into that. To avoid sort of the trap of having every integer object be sort of allocated on the heap and require lots of operations, we try to store integers unboxed without an allocation and a pointer using sort of the traditional language runtime hack of using the low order bit of a pointer to indicate whether it's really a pointer. And that works pretty well. So then the question is, how well did this work? And sort of if you go look at this MyPI runtime graph we made, it worked pretty well. It was pretty slow, and then it got real fast. So this was a big success. Here in this graph, this shows this happening in April. We actually turned on mypyc for most of the stuff we do about 6 months ago, but not this particular report generator. So really, this crater was back in October. So what's the future of mypyc? It was sort of originally built to be a pretty narrow accelerator for MyPI. And when we were designing it, we really wanted to make sure that building it would be justified just by the wins that we would get from MyPI. That just the speed up we're going to get from MyPI is worth building this. But it doesn't really need to always be just a MyPI accelerator. You could definitely imagine a lot of other typed Python programs that would maybe like a 4x speed up. So sort of the next thing on our roadmap is we'd like to try to get Black working under mypyc, and I think that's what I'm going to have my intern do this summer. We're also going to be working on mypyc during sprints on Monday and Tuesday, so if anyone is interested in hacking on code or documentation or trying to get their own stuff to compile with a typed Python compiler, come chat with me on Monday or Tuesday. And then MyPI is also going to be working on sort of usability error messages documentation those same days. So as the sort of TLDR for this talk, I've talked about how we've gotten to checking 3 million lines of annotated Python code in a few hundred milliseconds. Thank you. Questions?
We actually have 5 minutes. I'm sure people might want to ask something about mypyc to Michael.
Great talk. Thank you very much. My question is on the adoption side of things.
Yeah.
Have you had any luck? So at Instagram, we have a lot of developers very happy about type annotations subjectively. Mm-hmm. Occasionally, someone asks, so can you demonstrate to me using some data that adding all of these type annotations has improved something? Yeah. And I'm wondering if we usually respond with an awkward silence. I'm wondering if
no, that's exactly what we do. Yeah.
Okay.
We have anecdotes, but the thing is, it's very hard to prove anything about like the site outages that didn't happen. But every so often, we have a great example of like there's a site outage that wouldn't have happened if that function had had a type annotation. Like if this had been type checked, this bug would have been caught. And so we can sort of point to those anecdotes, but we don't really have data. And if you figure out how to do that data, let us know. And if I do, I'll give you a call too. Yeah, well, we have the survey, but that's just that we can prove that our developers subjectively like it. But we don't know how to prove that like it prevents outages or something.
Thanks, Michael. When you talked about static type inference, is that part of MyPI or is that a separate project?
Yeah, so it's sort of a tool integrated with the MyPI daemon. Then also in practice, when we use it, it's sort of a shell, like a bad shell script I wrote and some daemon code. So like the code is there for other people to try, but it's not quite a push button solution yet.
And kind of a follow-up, do you have a sense of like at what percentage of annotations something like that becomes like practical or productive?
That's a good question. Like I'd say just guessing, you probably want at least like 30 or 40%, or there's just not gonna be enough to start with. Like starting from an empty code base, you won't get a lot because it won't know where to start with for most things. Yep.
Very interesting talk, thank you. I have a related question to the type inference. So if I understood correctly, then you ran the inference process to then annotate the source code. I'm kind of wondering why. If you can infer it statically, then just keep that knowledge in the type checker and you won't need the annotations in the first place, right?
Yeah, so the inference system we're doing is this big, bulky whole program inference that's slow and sort of requires looking at everything. And so it isn't really something that we can plug well into the type checker because it's not like a traditional it's not the traditional type inference algorithm that you'd use in like a functional programming language or something. It's a much more sort of, let's look at all the like call sites to a function and figure out like, okay, here are the things it's calling it with. Let's just call it that and stuff like that. So it's not sort of built in a way where it could really integrate with that. And if it was, it would probably be too slow.
Hey, so if I wanted to use mypyc for like the typical, your code has one hotspot, so write that module in C, like how well does the tooling support that?
Reasonably well, as long as right now the big thing is that you can't subclass compiled classes from interpreted ones. And so if you've got some class that you need to subclass from other code, you're out of luck right now. But we definitely support that. You don't need to compile everything. And in fact, there's parts of mypyc that aren't, or of MyPI that aren't.
Okay, awesome.
Given your experience with mypyc, given a 100% type coverage code base, how difficult do you think it would be to target something like LLVM?
You mean instead of generating C?
Yeah.
The answer is that like it wouldn't be that hard. It would just be work. Like if you told me that it was important and it needed to be done, I could have it done in a month or something. But we sort of don't think it is. There's sort of nothing fundamental. It's just work.
I see. Thanks.
All right.
Thank you, Michael.